In Chapter 2, we're going to take a look at compounds. We're going to start by looking at ionic compounds in Section 2.1. Remember that a molecule is an electrically neutral group of atoms held together by an electrostatic force and considered a single particle. A chemical bond is an electrostatic force of attraction between atoms in a molecule. And remember, we've studied the different types of electrons, and that only valence electrons participate in bonding. These are only electrons in the outermost shell or energy level of an atom are the ones that are participating in any bonding. And let's review the octet rule. The octet rule states that when atoms bond together, they do so to achieve the special stability associated with having 8 valence electrons, except for hydrogen and helium, which will have 2 valence electrons. The octet rule states that atoms try to resemble electronically to the nearest noble gas. Remember that the noble gases have a complete set of valence electrons in their outermost energy level. For helium, this is 2 electrons, and for every other noble gas, this is 8 valence electrons. And the octet rule tells us that any atom can acquire this octet arrangement by either gaining, losing, or sharing electrons during bonding. So, chemical bonding actually makes atoms more stable, as they are fulfilling the octet rule. First, we're going to look at ionic bonding. Ionic bonding occurs between metals and nonmetals. Metals have very low ionization energy and therefore lose electrons. Nonmetals have high ionization energy and gain electrons. So when an ionic bond forms between a metal and a nonmetal, it is the metal that is losing the electron and giving it to the nonmetal that is gaining the electron. Generally, ionic bonds occur between metals and nonmetals where the difference in electronegativity is greater than 1.7. The nonmetal atom pulls valence electrons away from the metal due to a greater electronegativity value. Electron transfer occurs, sharing doesn't take place, a complete transfer happens. The nonmetal becomes an anion, a negative ion, since it gains electrons, and the metal becomes a cation, a positive ion, since it loses electrons. Since we end up with an anion and a cation, the two oppositely charged ions attract one another according to the law of electrostatics, which tells us that like charges of electricity repel each other, whereas unlike charges attract each other. Let's look at an example. Aluminum and oxygen metal and nonmetal in the pursuit of fulfilling the octet rule will gain or lose electrons. Aluminum has 3 valence electrons, and oxygen has 6. Oxygen would like nothing more than to gain 2 additional electrons to fulfill the octet rule. So the way this happens is aluminum will give up its electrons to oxygen. Now, you might have noticed for one atom of aluminum, and one atom of oxygen, you would end up with a single lone electron, and that's not going to be favorable for the aluminum atom. So we're going to have to add another oxygen. So we can give this to oxygen, but now oxygen is going to need another atom. So it's going to take a second aluminum atom, now we have 2 electrons that have not participated. So if we add a third and final oxygen, then we will have 2 atoms of aluminum, each of them has lost 3 electrons and has a positive charge, an overall positive charge of +3, and 3 oxygen atoms each of which has gained 2 electrons and has an overall charge of -2. So it's important that when you're showing the bonds that are formed or the electrons that are transferred between nonmetals and metals, it's important that you must show the electron transfer using arrows from the metal to the nonmetal. And show the resultant ions using square brackets. As we have above. So if this is a positive ion or cation, and this is a negative ion or anion, and they are oppositely charged, then the law of electrostatics tells us they will be attracted to each other and they will form an ionic bond between them. In general, at ambient room temperature, ionic compounds are crystalline in shape and solid in state. They're hard and brittle. They have high melting points and high boiling points. They are good conductors of electricity when dissolved in water and good conductors of electricity in the liquid state. Common examples of ionic compounds include sodium chloride and calcium carbonate.